Oh, we are on the last session, that is session 13 of our FDP. Participants, this is just for your information that your assessment link will be activating at sharp 6:30 p.m. It will remain activated till 7:30. So you have to appear the test by that time. If any issues arises for all the participants, then we will be doing some alternate approaches. But if it is like for most of the participants, if the link is okay, then we will be starting. We won't be taking any exams in other platforms. So make it sure with your net connections, and it is preferred that you will be attending the appearing for the exam only through ATAL portal. It is preferred that you'll be using your desktop or laptop for the exam, because we don't know in mobiles how your uh, paper will be coming, or question paper how it will be coming. Okay, so now it's our turn to call our next, or rather the very last esteemed speaker of this FDP. Just give me a minute. Dr. Arijit Mukherjee. Dr. Mukherjee is a principal scientist at TCS Research, specializes in embedding intelligence at the edge, focusing on low power, low latency computing and brain-inspired neuromorphic processing. After earning bachelor's and master's degree in computer science, Arijit worked in software industry before joining Newcastle University, UK, where he worked as a lead researcher in several UK e-science projects, contributing to the development of W3C standards for web services, SOA, and the concept of cloud. With a PhD in grid computing, he returned to Kolkata, worked in a telecommunications revenue assurance product company for 3 years before joining TCS Research in 2011. He currently leads research in edge and neuromorphic systems. A distinguished scientist awardee at TCS Research, Dr. Arijit has 75 plus publications in international conferences and journals, and 50 plus patents in multiple areas. So we welcome you, Dr. Mukherjee, and we are eagerly waiting for your presentation. Over to you, sir.
Okay, I hope I'm audible and my slide is visible.
Yes,
Just
yes,
confirm once. Yeah.
yes.
Okay, so I know this is the last session of a very long course. So I won't be kind of boring you with maths and all those things. This is practically a zero math slide, mostly kind of a storytelling on a very new evolving computing paradigm that's called neuromorphic, not neuromorphic computing. Okay, so as you know, the title is about being smart at the edge. So the first question is why edge, and what do we mean by edge? So you have all your mobile phones with accelerometers, gyroscopes, and other sensors. You have smartwatches that can measure your heart rate, measure your pulse rate, your activities and stuff. Uh, you have different things in and around your house which are smart enough to measure certain things within your house. You have the traffic cameras, um, checking the traffic flow. You have lots of different sensors and devices that are there in stores, streets, offices, which measure the environment, the surrounding. The thing is, as of today, all that these sensors are measuring, they are sent to a cloud. either enterprise cloud within the premises of a large corporate or a large industry, or to the external cloud, Azure or whatever cloud. That transmission of data from the sensors to the cloud, that takes time. So typically your turnaround time or latency is higher. It also spends energy because it's over the cellular network. So there is an energy consumption, that is the data transmission cost. Then it's never 100% reliable. So think of mission critical systems where drones and robots are monitoring a disaster situation, and you don't have 100% reliability on the network, because the network is, after all, a cellular network. Even it's 4G, 5G, 6G, it's still a cellular network, so cannot be 100% reliable. And think of medical scenarios like your body vitals, your heart rate, your pulse rate, your all other body vitals going over the open internet to the cloud, which is a severe violation of privacy. So these are the issues that are there, and people are now pointing out these issues, that you need to be able to have low latency, you need higher reliability, you need some form of inherent privacy, and you also need to avoid the transmission cost for sending data to the cloud. So edge is the answer. Compute in situ, on the device or near the device itself. But there are challenges over there because these edge devices, whatever devices, your mobile phones, your smartwatches, and all other devices inside your house, they are often low CPU, low memory. There are network and power constraints as well. Mostly they are battery driven. So edge computing, even though it's something that is desired, that people want to adapt, industry wants to adapt now, but there are challenges that we need to overcome. So this session is about how to be smart at the edge, how to process data on at the edge itself, on the net, on the device itself, by overcoming the challenges that we just discussed about. There is also another aspect, the cost of intelligence, whether it's edge and cloud. There is a cost that we always incur for training our AI systems to be smart, or to act in a smart manner. So I've given you some figures over here. If when a large AI models are trained, like the NLP models, the Gen AI models, they emit carbon equivalent to the lifetime of 5 American cars, starting from the manufacturing date of the car till the end of life, equivalent to 5 such cars. When GPT-3, the previous version of ChatGPT, was trained, it was trained on 45 terabytes of data on 512 NVIDIA V100 GPUs for 9 days. The total energy cost was nearly 28,000 kilowatt hours, whereas an average American household energy cost per year is nearly one third of it. Right. So when BERT was trained, BERT was the first version of Google's Gen AI. BERT was trained. It had a carbon footprint of roughly 1,400 pounds of carbon dioxide. That is equivalent to one trans-American flight, round-trip trans-American flight from San Francisco to New York or New Jersey. Now, if you train such systems with NAS from the scratch, starting with the data set, then you from the scratch build up an entire network. If you want to do it with neural architecture search, then that becomes equivalent, that carbon emission becomes equivalent to a completely full of passengers 747 jet. So that's cost in terms of numbers. If you just look at Google's search, so if Google is to change their search from their normal search algorithm to Gemini, just Google AI alone will be consuming energy, the amount of energy more than the entire country of Ireland. So these are the numbers that we are coming to know about how much energy current AI systems consume. So in 2050, this is a graph that was released by the Semiconductor Research Corporation. They are saying that the way we are computing now, going by this trend, by 2050, the global computing industry will be processing 10 to the power 42 to 10 to the power 45 bits per second. And that will lead to an energy expense that will be very close to the global energy production, which is bad. It is terribly bad. So you have to think about new ways of computing. One, uh, not, I mean, this 10 to the power 42 to 10 to the power 45 bits per second, that's a very, very, very high number. So can we reduce the number? Can we reduce our computation but achieve the same things like we do today? That is one. Second is, can we do something to reduce this energy cost? Can we process data or do the computation with less energy? Now let's take a look at the trend and the reality. Why this is happening? So the top figure, where you see the different modules like sensing, localization, perception, high level path planning, low level planning, and so on. This was the original way of computing. Say in case of this is taken from robotics. So that's what people used to do. So you had sensors. Based on the data, you would localize the robot. Then the sensors will perceive based on the sensors data and the perception inference. You will localize, then you will do a high level path planning, then you'll do behavior arbitration, low level path planning, then the motion controllers will take the robot to various places. That was the usual way of computing. Nowadays, the concept has changed. You have one single end-to-end model. It takes the input from the sensors. The model itself does everything. It localizes, it makes the high level path planning, it does behavior arbitration, it makes a low level path, and then it triggers the motion controllers to move. So the whole thing, everything happens in that one end to end model. Often we call these as foundational models, which are taking in lots of data, different types of modalities, and trying to process everything together. And what this has ended up is something like this. So if you go by that the amount of flops that the current models require. So starting from the advent of AlexNet back in 2012 or so, the way deep learning has progressed, you see the lower the gray line in the top graph over there. That's how deep learning progressed. The number of flops required for these state-of-the-art models, that increased by roughly 1.5 times a year, something like that, even less than that, not even twice. That was the original deep learning thing. Now in 2018, when transformers were released, the present day state of the art models, they are growing by 750 times every 2 years. So the flop requirement for the modern uh, models, AI models, they are growing by 750 times in every 2 years, whereas the Moore's law mandates that your processor speed can only increase by 2 times in every 2 years. Right. So that's the mandate by Moore's law. If you take a look at the memory, again, similar thing happened. Starting from 2018, when transformers came out, the memory requirement for these models, they have been increasing by 410 times every 2 years, whereas again, by Moore's law, the AI hardware memory, that has increased only by twice in every 2 years. So our processing requirement and our memory requirement both have increased in a extremely disproportional manner when compared to what increase we have achieved in terms of hardware. So our hardware, the memory, the processing speed, whatever things we have are totally outdated, or I should say totally not up to the mark that is required for the kind of computations that we are now doing, which is why all these energy costs and all those things come into picture. So Forbes in 2021 said that if we cannot attain sustainability, if we cannot make our AI sustainable, then the future doesn't become sustainable. So we have a bleak future if we cannot achieve this sustainable AI. So what we think are the roadblocks to low power computing and sustainable AI are these things, mostly the scaling problem. So again, in this graph, and if you go back to how we did computing, so starting from 1970s, uh, as and when the processor speed, the clock speed started increasing, our algorithm started executing faster and faster. That was the normal way. So we increased our clock speed, and our algorithms, the same algorithms, started executing faster. So this linear trend went on till about middle of 2000s, when this thing broke. This is called the Dennard scaling. By increasing clock speed, your algorithm executes faster in a scalable, linearly scalable manner. That thing broke by the middle of 2000s, sometime around 2005, 2006. That's when we started having the multi-core processors, dual core, four core, 8 core, and so on. That went on for some time till we reached that transistor size limit, the physical limit of the size of transistors that can be allowed in the fab, in the physical processors. So that limit was reached. That which means that Moore's law started flattening at that point of time, which is why in 2018 Global Foundries scrapped their 7 nanometer transistors. So you cannot put more transistor, you cannot increase the clock speed, you cannot put more transistors in your physical processor. So we are kind of in a roadblock. And all those things are happening leads to three major challenges that stops us from going into that era of sustainable AI. One is this flattening of Moore's law. We cannot increase the clock speed. We cannot make our transistor smaller. So that's the flattening of Moore's law. The second big point is all our computers of today, your laptops, your mobile phones, your desktops, your workstations, even the GPU workstations, all are von Neumann systems. So you have a CPU, you have a memory, you bring the data from the memory to the CPU for doing the computation, you write back to the memory, and you do it for every bit of data. Now, when that volume of data goes on to something like what we need in case of these AI systems, the modern AI systems, imagine those terabytes of data, 45 terabyte of data, every bit has to be pulled out of the memory to the CPU, processed and and be written back. So that creates a severe traffic jam or congestion on the memory bus that connects the CPU and the memory, which is called the memory wall or the von Neumann bottleneck. Now, because of this, there is heating, there are transistor limitations and this intense processing. So you have to cool down the system. So there is more energy requirement for the cooling systems. So the three major challenges that we have for attaining, prohibiting this sustainable AI. One is this flattening of Moore's law. Second is this memory wall rising out of von Neumann bottleneck, and the heat wall. There is a result of this von Neumann bottleneck. So the question is, can we do something that is non-von Neumann? Can we think of our computing systems in a different way compared to the von Neumann systems that we use today? So we resort to brain, trying to take inspirations from the brain, because brain is essentially a non-von Neumann system. By non-von Neumann, I mean where processing and memory are co-located in a single system. You don't have to transmit data between the CPU and the memory. So to begin that part, we take just a 60-second primer on brains. Why do we have brains? Plants don't. Still, the plants live. Sea squats, the top animal, that blue creature that you see on the top of your screen, they are hatched with a very elementary nervous system, and they swim from one rock to another, and then they just eat their nervous system, eat their brain, but after that they live. So from neuroscience perspective, it's said that animals need a brain to move, to find food, and to find partners. The brain produces goal-directed behavior to maximize the probability of survival. That is the theory of brain. Now, to understand brain, to adapt the brain way of computing, we have to figure out what brain does in a very efficient manner. So the brain way of computing depends on three things. One is the algorithmic efficiency of brain. The second is the anticipatory and semantic concept of brain. And the third is this adaptive learning and invariant representation that brain performs. So let's say this algorithmic efficiency, why the algorithms that we have inside us are more efficient than what we can provide to the computers. So let's say, let's take an example of scene understanding. If I show you this picture, it will take you maybe less than 10 seconds if you are from Kolkata to tell me that this is a picture of the Victoria Memorial. If you want to do the same thing with a computer, an image processing program, that program has to first go through this image pixel by pixel, then figure out that, okay, this is a building, this is like a palace, and then it has to match against a huge database of images to find out that this has similarity, 90% or 95% similarity with Victoria Memorial. So it's most likely that this is Victoria Memorial at the time of task. Fine. So for it will require maybe 100,000 lines of code to be processed to understand this whole thing. Whereas in our brains, when you saw the picture and when it reflected inside your brain that this is an image of Victoria Memorial, that whole thing took just between 10 to 100 synaptic stages. Just 10 to 100 synaptic stages. Compare that to 100,000 lines of code being executed on a computer. Till date, we have never been able to write an algorithm as efficient as whatever happens inside our brain. That is one. Second is, apparently there is one single algorithm that works in our brain. So this was found out by several neuroscientists who did an experiment on neonatal ferrets. Ferrets are a species like squirrel, like small rabbits. So in several laboratories, 4 laboratories actually, they did an operation, invasive operation on these ferrets, newborn ferrets. The idea is your eyes are connected to a portion inside your brain called the visual cortex via the optic nerve. So whatever you see, the image from your eyes travels via this optic nerve to your visual cortex and you see something. Similarly, from your ears, the sound waves travel over the auditory nerve to your auditory cortex where you see things. Normally, you will think that, okay, my visual cortex is meant for seeing, so there is an image processing algorithm running over here. My auditory cortex is meant for hearing things, so there is some sound processing or sound wave processing algorithm running over there. That's the normal case. Everybody will think like that. What these neuroscientists did was they severed the connection between the ear and the auditory cortex and they connected the eyes with the auditory cortex. So instead of the optic nerve connecting the eyes with the visual cortex, they rerouted this optic nerve to go and connect with the auditory cortex. Now, if you go by this idea of having different algorithms, image processing algorithm in visual cortex and sound processing algorithm in auditory cortex, you'll feel that, okay, the neonatal ferrets will die because they won't be ever be able to see. But that's not what happened. Within a month or so, the neonatal ferrets were able to see things via their auditory cortex. So the neuroscientists say that, okay, so there must be only one algorithm that works in our brain in different zones, whether it's visual cortex or auditory cortex, doesn't matter. It's the same algorithm that runs everywhere. It behaves differently when it gets different types of data. So there is one algorithm that processes different types of data differently to end up in different kinds of perception or senses. This led to this hypothesis of one algorithm. So there's one algorithm inside our brain. Till date, we are still searching to write that one algorithm that can be processed on computers to do things the way we do. Uh, that's the algorithmic efficiency part. Then this anticipatory part. Brain performs based on anticipation and previous experiences. Previous experience in the sense is when, let's say, I am talking about all these brain things, you are hearing some sounds, that sense connects back to your learning of words in your school. That sense connects again back to your learning of alphabets in preschool. That sense connect back to your learning of sounds to your babyhood. So all these concepts are related. Let's say if I do a very bad mimicry of Twinkle Twinkle Little Star in a broken voice, you'll still be able to recognize that because it hits a memory that you acquired when you were a kid. Now, if somebody renders the same tune with a whistle or a mouth organ or a piano, even makes incomplete rendering of the tune, you will still be able to relate it with that experience, and you can anticipate what's going to happen next. So that way of computation, we still don't know how to do it in case of computers. And the semantics is another funny thing. It happens for words, and brain stores words related to with a mapping of the context. Nowadays, Gen AI does that to some extent, but not fully. So in case of brain, it's like the same word. Let's say hot. Hot has different contexts, right? So hot can be a food that is very hot, means temperature of the food is very high. The food can be hot in the sense that the food is very spicy. The weather can be hot because the temperature, the external surrounding environmental temperature is high. Or a thing, let's say a glass can be hot because the temperature of that object is high. Or let's say a person can be hot because the person looks very nice or something, so the person can be hot. A movie or a book, everything, all these things can be hot in different senses because depending on the context, on the subject and the context. Brain stores each of these in a separate area of itself. So the hot related to spicy food is stored somewhere, the hot related to temperature hot stays somewhere else, the hot related to a person looking very smart stays somewhere else. But we can very easily dig out that actual meaning based on the context, which which will be troublesome for computers. GNA, as I said, GenAI can do it to some extent, but not as efficient as us, not yet. The third most important criteria, or third most important feature of brain is the way it represents things in an invariant manner. So let's say this image, this is that of the Bishwa Bangla Gate. You can recognize that image of Bishwa Bangla Gate or Victoria Memorial, even when it's night, even when it's dark, even if it rains, if it snows, whatever it is, you can still recognize the image of something, because in your brain that is stored in a way that is invariant of the surroundings, that is the light conditions, the color conditions, the weather conditions, all these things, they do not matter when something is stored inside your brain. Whereas if you want to teach a computer to be able to distinguish things in different light conditions, that's a big challenge, right? So that is one. And the other is called synaptic plasticity, which means when we see things or do things, hear things, there is a kind of circuit simulation that happens inside our brain, and that those circuits get stronger and stronger when you do the same activity over and over. So your learning becomes permanent. In Hebbian learning, it's said that neurons that fire together wire together. So when you do something or hear something, some of the neurons inside your brain get activated, fire, and they wire together to create that circuit, which gets strengthened over time. Fundamentally, these are the things that brain do, which is why supposedly brain is much more efficient in certain aspects, like visual audio comprehension, navigation, route planning, decision making, do all these things from very limited amount of data. Not like you feed billions and billions of images or documents to a AI system to make it intelligent. It's not like that. Think about when you learned to distinguish between cats and dogs. Probably you have seen 5 or 10 cats and dogs, and then you started being able to differentiate between them. Computer needs maybe 100,000 images of cats and dogs to be able to make this differentiation. Still, the computers are better in terms of computational ability, speed, memory access speed, memory lifetime, capacity, accuracy. All these things are better. Computers are faster, even though, sir, for certain things, our perception, adaptation, flexibility, cognition, learning, innovation, these are more efficient than all the computer systems of today. All these things happen in the brain in a very energy efficient manner, Firstly, because brain can process data in a very sparse manner. So data sparsity doesn't matter to brain, because rather it's the inherent feature of brain. Brain doesn't need every pixel of an image to be processed to understand what that image is. So this is an image. This is a story of this e sensors or electronic retina that was created by Misha Mawald and Carver Mead back in 1991. They scientifically proved that when we see an image of anything, say, let's say a cat, actually this is how the cat appears inside our brain. You don't need to be able to process every pixel. You just typically process the pixels for which change at a given point of time. So the change in luminosity of a given pixel at a given point of time, that is only what your brain needs as an information to be able to process what the thing is. Let's say in this case, the right hand side picture, so that is there's a guy with his daughter and a dog playing with the dog. This is how the electronic retina will capture the image of all these things, given that everything else is kept still. It doesn't consider all those pixels that are not changing. It only captures the pixels which are changing at a given point of time. That's exactly what our eye does, and this is exactly what modern day dynamic vision sensors, the most efficient sensors for vision purposes, also does. So this is the left hand side is May 1991. The right hand side, you see a dynamic vision sensor that is present days electronic retina. Uh, we are very good in, as I said before, we are very good in navigation and route planning. That happens because there is inherently a mapping system that resides in our brain. Uh, let's say, I'll show you this experiment. So this was an experiment that was performed by John O'Keefe back in 1974. So he inserted some probes in a rat's brain and allowed the rat to move inside a black box. And he figured out that whenever the rat is crossing or recrossing a given location, exact location, certain neurons inside the rat's brain are firing. So every time, it happens to you as well, every time you go back to a place that you have visited before, you know that this place is a known one. You have visited this place before, because certain neurons that got activated when you went to that place for the first time will get activated again when you go to the same place the second time or the third time or the fourth time. So certain neurons inside our brain are able to relate to the memory of a place. So John O'Keefe called these neurons place cells because they can map or they can match a place. So place cells. 30 years down the line, his students, Edward Britt Moser and um, May Britt Moser, they did further experiments on the same setup, and they deduced that whatever those patches of that those white patches that you are seeing, the place cells, they are kind of look like a rudimentary hexagon or a triangle. So they deduced that in our brain, the coordinates, the spatial coordinates are mapped in terms of hexagons, and which is why we are always able to locate ourselves or localize ourselves in a given space. When you are standing in a room, when you are standing in a large space, say in an open stadium, you can always more or less efficiently localize yourself that you are standing at a certain position in that spatial grid. This happens because our brain has this inherent mapping system, inherent GPS. There are similar other cells, border cells, head direction cells, speed cells, doing different things. Now, why I'm talking about this? Because this is how our brain computes, and this is what scientists are trying to use now. So Google's DeepMind, they tried to use the same idea to figure out if an agent, computing agent, can navigate inside cities using this concept of grid cells, place cells, border cells, and so on. So think about the way we navigate. Usually before we had this Google Maps, we did our navigation based on landmarks. So I'm standing at some place, I know the landmarks, there is a shop there, the name of the shop is XYZ. From here I take a bus and then I go go east or north or south. Then I see a monument, there I see a stadium, things like these. I know all these landmarks. I navigate based on that. So they taught an agent, a computing agent, to navigate a city based on the such landmarks that appear in the Google Street View. So if you take Google Maps and you drop that little man on the street, you'll see images of the street, images of things around the street, shops, monuments, other things that are there on those streets. So they took these images and trained this system so that the system becomes able system the agent gets to navigate a city using these images as landmarks. And they trained that agent on the data from New York, and the agent was able to successfully navigate in a similar manner in London, Paris, Moscow, everywhere. So it's possible to train a system using these concepts of the brain, and let the systems perform things instead of doing in the traditional way, in a more brain inspired way. So why is brain becoming so important? Because as I said, that no, traditional computing systems consume huge amounts of energy, whereas brain performs all these things that the computer systems do: write an article, recognize a picture, talk to somebody, or answer a quiz question. All these things that AI systems get cheered for doing well, like writing an article. When GPT-3 wrote an article, people said, okay, AI has reached a stage, but at what cost? So brain is able to do all these things in a much more energy efficient manner, because the von Neumann systems consume more power, and these non-von Neumann systems, like the systems that we are going to talk about today, the neuromorphic systems, they are more brain-like in the sense that they co-locate computation and memory in the same area, in the same cell. So think about neurons and synapses connected together in brain. The neuromorphic systems are architected in the same manner, and and they can perform well by localizing, by removing that entire data transmission cost. Now all these things happen through spikes. As I said, brain processes sparse data. So that data, the type of data that brain processes, are actually spikes, like you are seeing in this GIF, electrical spikes. These spikes happen in the brain because of some electrochemical process that inside our neurons. I'm not going into the details of that, but everything that you do from your childhood, from your birth to your old age, are actually the result of these spikes. Typically, your life is built around 34 billion cortical spikes. Everything you do from your birth to your old age is about these spikes. Now, what are these spikes? As you can see in these videos, they happen at a given point of time. When some stimulus happens, when you see something, hear something, there is a stimulus. That stimulus activates the neurons of your brain, certain neurons of your brain, which fire at a given point of time. And that's when these spikes happen. The spikes move to the designated area of your brain and you perceive something. So as you can see, that those spikes are sparse. It doesn't happen all the time. It happens at certain intervals. It's less in number. You don't have to process, as I said, you don't have to process every pixel of an image to understand what that image is. You can understand what that image is based on this kind of sparse information, which is exactly what happens in neuromorphic systems. Neuromorphic systems, as I said, are architected like mammalian brains, where computation and data are co-located in terms of neurons and spikes. Neuromorphic systems operate on sparse data in form of spikes, which is why the data volume is less. Because of these two reasons, co-location of computation and memory, and the ability to process less data, sparse data, results in around 1,000 times of energy savings in case of neuromorphic systems. So most neuromorphic systems are around 100 or more, close to 1,000 times power efficient than all your traditional systems. Uh, so this is how things happen. You see the spike GIF on our brain. This appears as a train of spikes, like this middle image here. The blue lines, these are the spikes. And in case of brain, the timing of these spikes are important, not the amplitude of the spike. So whenever the when did that spike happen? For every activity, there is a train of spikes for, and all these spikes happen at given time interval. So that time period is most important. uh, Currently there are few neuromorphic platforms under research. uh, Not all of them are commercially available, only very few are. So this brain chip Akida on the top left hand corner, that is one commercially available neuromorphic chip, but you won't be able to buy that off the shelf from any vendor. You have to talk to the manufacturer, have to go through some kind of collaboration agreement to get hold of one of these chips. Intel is making a chip called Loihi, and based on Loihi, this Hala Point is the largest neuromorphic research system with a few billions of neurons inside it. There are smaller systems like from Simpsons, Spec, and Xylo. The whole thing actually started from the Human Brain project that was running between different universities. EU project like in University of Manchester, University of Heidelberg, and so on. So University of Manchester came up with a digital version of huge supercomputer, which is brain-like, which is called Spinnaker. And University of Heidelberg created the analog version of it called BrainScale-S. There are other smaller companies like Inatera, which has created a neuromorphic chip called T1. Then Spikey from Heidelberg. There is Prophecy. There is Zeroth from Qualcomm. There is BlueMind, which is an analog chip, and Kaspersky is that computer security firm which who creates these antiviruses. They are also creating a chip called AltAI. So these are all these chips are kind of research platforms which are people are doing experimentations on them, including we are also doing experiments on them, trying to achieve this smartness that I talked about in the beginning. That smartness, the ability to infer data at the source, on the sensors itself, on the devices itself, using these chips at a very low power footprint, low energy footprint. Theoretically, these neuromorphic systems lie at the intersection of machine learning, neuroscience, and competitive computer architectures, or this computer architecture and organization, three subjects. So like your AI and deep learning systems, all are actually a subset of machine learning. We are taking the whole set machine learning. We have to borrow ideas from neuroscience, because a lot of these things actually are related to the brain, the way brain performs, mammalian brains. Neurons are more bioplausible, not like the perceptrons that we use in deep learning systems. So there are bioplausible neurons. So we borrow from neuroscience, from machine learning, and these competitive architectural systems. To that is the intersection is the neuromorphic systems, where we create neural networks, similar kind of neural networks like you have studied about, but with different neurons that are more bioplausible. We call them spiking neural networks, often called the third generation of neural networks. And we do different types of work on them. Different types of functionalities can be achieved. Different applications can be run on these systems. So people have been able to convert normal ANNs into these spiking neural networks. You can do different forms of SNN backpropagation, but it's still on something under research, because as you can if you recall, the spike is a uh, it's a spike for a very short duration, right? Just like an electrical spike happens just for a split second or something, and a spike that way is not differentiable. And all your back propagation, the learning rules in neural networks, depending on back propagation, depends on the differentiation of the error values. You cannot do the differentiation of spikes because spike has a time duration of basically 0. So how do you approximate back propagation in case of SNNs? How do you make these SNN systems learn online from limited data? Then all these different kind of ideas that came from neuroscience, olfaction inspired rapid learning. Rat slam is a navigation algorithm, slam, simultaneous localization and mapping that is used in robotics, but based on how rats do mapping and localization. The idea is taken from a study of rats brain. Then cortical microcircuit models trying to figure out whether the kind of diseases like Parkinson's and Alzheimer's and all those things. Then people are also using these spiking neural networks for large scale optimization problems like traveling salesman, vehicular route planning, or graph search problems, hyperdimensional computings, all these things. These are also happening in the research world. This is one benchmarking information which I'll just skim through. So people try to do benchmarking of these neuromorphic systems. This is important if you want to see the extent of power savings that neuromorphic systems can achieve. So these Hey Siri and OK Google kind of keyword spotting applications, they were run simultaneously on Loihi system from Intel, which is a neuromorphic system, and a neural computing stick from Movidius, a Jetson system, a CPU, and a GPU. Jetson obviously from NVIDIA. And you see the the energy expense, the lowest part, the smallest, the tiniest one is the neuromorphic system, Loihi, and the largest one is obviously the GPU. The right-hand side graph is about energy efficiency. The bigger the circle, the more energy efficient the system is. So on the top left-hand corner, the tiny circle is that of GPU, that is the least energy efficient, and the largest circle on the right-hand side is that of Loihi, that is a neuromorphic system. So what do we do at TCS? TCS research on neuromorphic. So we work on these neuromorphic systems for various kind of applications, action, gesture, recognition, time series classification, prediction, image segmentation classification, lossless data compression. We use different kinds of platform tools, different architecture like libraries like feed forward, recurrent, reservoir, spiking, and all. Different types of learning algorithms like ANNs, STDP. STDP is a standard learning for spiking neural networks called spike time dependent plasticity. We use hardware. We have a real hardware from Brain Chip, this Akida chip. We are also working with Intel and since trying to get hold of the SynSense hardware. And at IIT Delhi, one of our research collaborators, they're trying to create a in-memory neuromorphic chip that will be able to monitor incoming packets, incoming network packets, and flag out if there is an anomaly online, completely online. So these are the things that we do. We are seventh in terms of IP globally, and we are the only large commercial org in India working in this space. So I'll show you some small demos of how things work in neuromorphic. This is one of the object recognition demo that we did for this Akida neuromorphic chip. So what we do essentially is we show the system, the network. It's a standard neural network. We show it certain objects and tell the system that, okay, this is an object A. So for example, let's say we'll show it a pen and tell that, okay, this is a pen, and we'll show only one object of the class. So let's say this is a cup. We are showing the system a cup and telling it that, okay, it's a cup. We just showed one cup. We showed one marker here, just once. Then one book, right? Then one bottle, and then one trophy. Now, if you are actually being able to see the video, you should be able to see the amount of energy that it's consuming, around in millijoules, 8 point something millijoule per frame. Now we are showing it a completely different cup or a different bottle. It will still be able to recognize from that one single instance that we showed it earlier. So ideally, this demo shows two things. One is the amount of energy that is in 8 point something millijoules per frame, and the second is the ability to learn systems from a very limited set of data with just one or two examples are good enough for this. So this is one. Second, we worked on gesture and action recognition. The left-hand side is our first venture with brain chip. We demonstrated this at NeurIPS 2019. So here we showed some gestures to a robot via a dynamic vision sensor, a DVS camera, and the robot was able to learn the gesture in just 3 to 5 seconds. And the energy consumption here was for the 200,000 events that were processed per gesture. The energy consumption was less than 3 milliwatts. Based on the gesture, it was able to perform different actions. We did the same thing, similar kind of thing on for human robot collaboration using IBM DVS gesture data set, achieved around 95% accuracy on that. We tried the same thing with radar data. So DVS gesture data set is already in the spiking domain. It's captured by dynamic vision sensors, right? So it's sparse data. Now, in case of radar, why we use radar is an interesting point, because elderly people are they often live alone, and then they need to be monitored for any kind of act, whether they have fallen down or how they are staying in those old age homes. But they don't like cameras to be put inside their homes, right? So a camera is a strictly no-no. But these microdoppler radars, they can kind of catch the actions that you are performing. So if for every action, the microdoppler radar will catch a signal. If that signal can be processed using a neuromorphic, we processed that signal using neuromorphic systems, and we were able to match the accuracy of state-of-the-art machine learning systems. And it was also very power efficient at the same time. We applied the same concept for hearing people with people who are visually impaired. So if you do air writing in front of people who are visually impaired, they'll still be able to figure out what you are writing. Let's say you write, "I am a boy" in air in front of a visually impaired person. They will be able to hear the disturbance that your hand movement is creating, and from that, they can figure out what you are writing in the air. So we did this with a very cheap microphone array. So in front of the microphone array, people performed that kind of air writing, and the system was able to recognize what was written over in the air. Neuromorphic systems are very efficient or very useful in case of wearables and medtech, like your smart glasses, smart watches, smart whatever things that have the medical applications like heart rate, pulse rate monitoring systems. So I'll tell you about this ECG monitoring. So why we need to do ECG monitoring on neuromorphic systems? Because the neuromorphic systems are, let's say you have a ECG monitoring device, a chest band, a chest strap, and you don't want to send your heart rate or ECG rate over the cloud to the hospital or to the doctor. So your chest strap should be able to figure out whether you have any problems in your ECG or not, whether you have atrial fibrillation or not. That also should not consume the battery of these ECG chest straps. So you should be able to do remote sensing on the chest strap itself in an energy efficient way. So that is something that we did for the different data sets. The next focus is trying to do the same for um, rate responsive cardiac pacing, which is another interesting use case from the medtech industry. Rate responsive cardiac pacing is for pacemakers. So you have many people have pacemakers, and the pacemakers are designed to send a signal to your heart to beat at a certain rate, right? Now, typically these pacemakers send this signal at a constant rate. It doesn't adapt to the kind of activities that you are doing. So let's say you are walking up the stairs, your heart is already beating fast. You don't need the heart to beat in a faster manner. You need to make it slow. The heartbeat should slow down. because you have just gone up the stairs and your heart is normally beating faster. So in these cases, the doctors are saying that if the pacemakers can be made to understand the kind of activity you are doing and then adapt to that in terms of sending the signal, it becomes useful for them. Now, to do that, you have to kind of try to understand the activity, your heart rate, and all those things inside the pacemaker itself. Typical pacemaker, the battery life is about 7 years. When you do all the inferencing within the pacemaker, the battery life drastically shortens down to 4 years. Now, when if you have to change the battery of a pacemaker, you have to go to surgery, and every surgery increases the risk of infection by 10%. Now, this is a nightmare scenario for patients, for healthcare providers, for insurers, for hospitals. That's why they're trying to come out with approaches where to see whether it's possible to run these kind of features, inferencing algorithms inside the pacemaker itself, to make it suitable for all the person based on their activities. We are working on a neuromorphic for space, that is edge in space. So mostly for smaller satellites, which are of the size of a tissue box often, maybe a bit larger than that. 10 centimeter cube are the typical dimensions of these CubeSats. And 10 centimeter cubes size satellites means you can well imagine that they don't have large power cells, they don't have large solar panels, so energy harvestation is also limited. So when these satellites are sent in space, what originally happens is they take all those earth monitoring images, ground images, to detect forest fires, oil spills, and all those things, and they have to send in the entire data set to the ground station at on the earth, and they have to send everything within 20 minutes, because that's about the duration for which the satellites have visibility of the ground station. So that's a limitation in case of these satellites. Now, what happens is when you take images of these of Earth from the satellite above, statistically it can be seen that around 50% of the images are cloudy, non-usable. They are so cloudy that you cannot figure out what's there inside the image itself. So if you are actually sending data that is junk to the observatory or the ground station, then you are actually wasting your bandwidth, you are wasting your energy. So the idea is, if can we process the data at source, that is when you take the image on the satellite, can you actually see whether the image is usable or not in terms of the cloud cover? If you want to do this on the satellite, then the challenge is you have to do it at a very energy efficient manner, because the satellites themselves are restricted or constrained in terms of energy. So we use the same similar neuromorphic systems inside satellite inside this, and we achieved around 35 to 230 times more energy efficiency compared to standard Jetson TX2, and 3 to 7 times lower latency compared to Jetson TX2. And we were actually able to compress the entire image on board before sending to the ground station. We achieved around 10 times lower energy consumption compared to 7Z, and achieved around 50% compression, which is more compared to state of the art compression techniques. So the takeaway essentially is that these evolving neuromorphic processors, they are designed to replicate the human brain, which is critical if you want to enable intelligence at the edge. And you can process data in a very low latency real-time operations. You can perform low latency real-time operations, and your energy cost is also less. These are far more energy efficient compared to traditional computing systems. And there's a white paper over here. I know you cannot see the QR code. If you just scan the QR code, you can see the exact work that is being done here.
Hello, sir.
Oh, I got muted.
Yes, sir.
Okay. So this is the kind of if you can see this LIF, this is a special neuron that we use in case of spiking neural networks. LIF means leaky integrated fire. So unlike the neurons that you have in your traditional artificial neural networks, there is a more bioplausible version of a neuron called leaky integrated fire. There are other things, but we use this for simplicity. So this is how spikes appear, right? This is a simple code that tries to encode the MNIST data, the handwritten digit data, MNIST standard MNIST data. It tries to encode the data in form of spikes. This is how it looks like, a spike. And I had a, yeah. So let's say this one. This is 0, right? In MNIST hand coded digit, this is 0. This is the, when you feed this 0 to the spiking neural network, it appears to the spiking neural network as this is the spike train that I was talking about. Or given point of time, and you have all these neurons, it appears like this. These are spikes at given point of neuron at for those neurons. This is what is sent to the spiking neural network, and this is how it processes the data. Let me just run one system for you so that you are able to actually experience the whole thing and maybe appreciate it more. Yeah, so this is SNN torch. This is basically a simulator which you can use. So let's say I run this. Okay. So as usual, you run all your standard import operations and data set downloads, which are very pretty much standard. If you know deep learning, you can do these in seconds. Then you import the classes and stuff. You create data loaders. Now this is how encoding happens in case of MNIST. So this is the fun bit. So when we read the encoding the input data from MNIST, if you see this part, the converted vector that appears that we are using is actually a series of zeros and ones, nothing more than that. So that is the point here. Spiking data means data only which is zeros and ones. You don't, all your real value data has to be converted into zeros and ones to process via these spiking neural networks as SNN. So this is how it happens. Sorry. So this is one, right? This is how the input goes to the spiking neural network. See, it's saying that the corresponding target is 1. It's able to recognize that this is 1. This is how things happen. Yeah. So this is what I wanted to show. So on the x-axis, you have the time step. On the y-axis, you have the neurons. So we have around 700 neurons in this network. And each dot here represents a neuron, that particular neuron. So for example, this dot here is probably the 380th neuron or something. At each given time step for that number 1, for these given time steps or time instances, these are the neurons that fired. So this is what happened actually inside this network. This is what is happening inside your brain as well. Now this is for a number 1. When you are seeing something, some book or something, reading something, a sequence of these such things are happening inside your brain. Exactly that this, we are trying to replicate that thing in a computer system, so that we end up processing less amount of data. We end up processing the data more efficiently, because there is no data transmission between CPU and memory, which is why our power, the energy efficiency of our brain is greater than computer systems. And we are trying to replicate the same thing using neuromorphic systems. So the computing systems also can be able to process data in a more energy efficient manner. So that's the kind of the end of the talk. Yeah, that's all. If you have any questions. Okay, doesn't seem to be any more questions here.
Sir, there is probably one question from one
Yeah,
participant.
please.
Hello,
Yes,
Sir,
Kaushik Mandal, sir. Yeah,
yes, sir. Sir, how we will do this kind of research at our organization, sir?
it's nothing rocket science. You
Now,
can
but the chip is required, right? As per
not really. No, you can start without the chip. You can start using SNN torch. You can start using rock pool. You can start using the simulator that is provided by Intel, which is lava.
okay.
uh, there are
So,
different ways.
any requirement dot text kind of files are there with you, means so that we can start with, means these packages are required for this
No,
neuromorphic.
each of these systems have their own set of requirements. So
Oh,
better option is, let's say the more easiest one of them is SNN torch. It doesn't require any chip. It's purely a simulator. So just look for SNN Torch in Google. Go to the SNN Torch website, and when you install
okay,
SNN Torch, pip install SNN Torch, it will download all the dependencies that you need, and then
right.
use Jupyter Lab or anything to go through the
Yeah.
examples that they provide, and you can start using it. And once you are through with SNN Torch, or just get an idea of what the whole thing is, you can go to Rockpool or Intel Lava, anything like that. You don't need the chips right now.
But there is a possibility to means change the parameters in their coding, right?
Yes, exactly. So,
But what about
like
the computing architecture that is sensing that neuromorphic transition?
which architecture? The network
That
architecture.
yes, sir, yes, sir. The
You can create your own
circuit
networks.
architecture.
You can create your own networks like you do for ANNs. You can create your own networks using SNN.
But the same network which is embedding inside the chip, that is
No,
available for us or not?
it's not getting embedded inside the chip. That's the beauty. It's a non-von
Okay,
system, a chip
okay,
that emulates the brain using neurons and synapses as the processing entities. Instead of a CPU, you have neurons and synapses doing the computation.
okay. There is no north-south data exchange like kind of thing up there. So how they are exchanging the data inside their chips, then?
Like our brains do, the data exchange happens. The synapses are the intermediate stores of data, and the neurons are the processing entities. So you
Okay,
just pass spikes through neurons. The neurons activates, or either the neuron will fire or not fire. That bit of
okay,
information is stored in the synapse. That's all. And it
okay,
creates a weight. The more you train, the weights are stored in the synapses.
okay, 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 sir. Thank you.
Anything else? There is another hand
Sir,
raised.
another question is
Yeah.
there, probably from Arup Dasgupta.
Yes, please.
Uh, Sir, am I audible?
Yes, you are.
Sir, this is a question from a very layman's sort of thought, not a technical question, from a
Hmm.
very layman's thought. At the very beginning, when you were talking about that neuroplasticity and the brain structure, something, and you showed that Victoria Memorial picture at dusk, something that came to me is that the brain makes so many mistakes. It is so easy to fool the brain, especially the visual thing. We have seen all those visual puzzles and all where the brain thinks that parallel lines are not parallel. We have all had experience when we recognize a person, then we go and find it is a different person altogether. And lots of our senses gets fooled all the times. So
Hmm.
while the brain processing is very efficient and very good for working with incomplete data and drawing decisions from that, our real life shows that brain also makes, our neurological structure makes a lot of mistakes.
Yeah, and
So
brain
when
learns
we are
from all these
borrowing that
mistakes,
structure
right?
into our neurographic processing, how can we prevent that, the negative, borrowing the negative part also?
See, brain makes mistakes, but brain also learns from the mistakes. So if you think about reinforcement learning, that's how you learn, right? The systems will learn. The making the mistakes that brain makes, like fooled because of all these illusions and stuff, they are actually trying to prevent certain signals going inside your brain. So those signals are prevented at your sensing layer. Your eyes are not seeing the signals properly, which is why those signals are not going into your brain. Here we are not using human sensors. We are using sensors that are electronic. So they are actually gathering the actual data, and the actual data is going inside the network, which is why the illusion is not likely to happen or shouldn't happen.
Yeah, so even beyond illusions, there are other things, our memories that are stored in brain. Generally, from what little neurological thing I understand, those memories do get corrupted, morphed.
Yeah, so
They merge,
we are
often
not
in
using
unexpected ways.
we are not using that physical memory. We are still using an electronic memory, which
Uh,
have the memory
so,
capacity and all those
so
things are
hopefully
better.
this, right. So
Only
hopefully
the
our
processing
electronic
happens.
stability will prevent this type of thing.
Yes, only the processing happens in a brain-like manner.
Right. So we are borrowing just the neurological processing part
Processing
mainly.
part.
Okay. Thank you, sir.
Yeah. Anything else? If not, then I'll just stop here. Okay. Thanks everyone.
Thank you, sir.
Yeah. Thanks. Bye.
We think sir has lost his network connection. So participants, please bear with us. He will be joining soon. Um, it's a small announcement again. Your please check your assessment portal. First, you will be checking your attendance. If your attendance is 80%, then your assessment tab will be activated. Otherwise, not. To get certificates from ATAL Academy, you have to score 70% in the attendance. Minimum attendance criteria is 80%. once all the things are done, all this like assessment is done, then you have to submit a feedback form in the ATAL portal. Then only you'll be getting certificate, or rather you'll be eligible to get the certificates. So thank you. Just wait for few more minutes. I think sir will be joining soon.
সেটা কি করে বোঝা যাবে বলো? তুলে তাহলে বাটিতে রাখবে, ওইভাবে থালাটা ইয়ের মধ্যে রেখে দেবে না, টেবিলের মধ্যে নোংরা করে।